So, we will start considering the spin angular momentum. So far what are the quantum number we have seen? That is n, that is the principal quantum number. Okay. So, it can take value 1, 2, 3, 4, 5 and corresponding is 1, 2, 3, 4, 5 etc. And this we tell this K shell, L shell, M shell, N shell, right. And then angular quantum number, azimuthal quantum number. So, this is the better we should write, because we have another quantum number, that is the angular spin quantum number. So, this generally we tell this orbital angular quantum number. So, this L value it takes for a particular n value, it can take 0, 1, 2, 3, 4 etc. So, its name is given as P, D, F, G etc. Okay. So, then we got the other quantum number. So, the spin quantum number, this is also angular momentum, spin angular momentum, orbital angular momentum. So, spin quantum number, and this it can take value half, it can take value half. Okay. And then two more quantum number we have seen, that is basically active, for when we apply magnetic field or electric field, some external agency we apply. So, that one was the, I will write that one later on. One is ML and another one is MS. So, corresponding here ML, MS are there. So, that's about a fixed direction in space. That direction is generally taken the direction of the external magnetic field or electric field. Okay. So, that I will come later. So, without magnetic field or electric field or external agencies. Okay. So, what are the quantum numbers? So, these three are the quantum number. Okay. Now, we have seen the quantization relation. This for L we have seen, L angular momentum, it is quantized. So, it is L H cross, L is magnitude, okay, and L can take value as I told, and then similar S we can write similar way, S H cross, S can take value half. So, here this L angular momentum. So, this basically electron. So, its direction of the angular momentum is you can take this L, okay. And this L now it is for a particular orbit, it is fixed, it is normal to the plane. Now, then we have seen this now orbit, this in space is quantized, so it is giving ml. So, that I will come later. Now, in case of S also electron, okay. So, it has spinning motion and for that the spin angular momentum. So, it has also direction S, right. So, now for same electron there are two angular momentum. Now, question is that whether they are independent or they are coupled. Okay. Actually, they are coupled. It is called LS coupling. It is called LS coupling. LS coupling. So, L and S they are not independent. They are coupled together and give the resultant angular momentum. So, when they coupled, they give the resultant angular momentum. So, that is that called total angular momentum. It is represented by J. It is represented by J. Okay. So, L, S and J. J is the total angular momentum. And representation of the J is basically it's so I will not draw this orbit. So, one electron it is in orbit, it has angular momentum, orbital angular momentum, spin angular momentum, and then due to this LS coupling we will get the total angular momentum. So, how they are coupled? The question is how they are coupled. So, that we can consider that. So, this electron, this the say orbital angular momentum, and say this the spin angular momentum. Okay. So, now they are coupled and the resultant J. So, these two are vector basically, right. They have direction and they have magnitude. Magnitude is half and this L have different magnitude depends on. So, now say it is L magnitude. So, now resultant one. So, from vectorial addition we can get this resultant angular momentum. So, that will be basically this. Okay. So, that is J, that is J, let me write here, that is J, okay, that is J. So, from vectorial addition we can get the resultant angular momentum. So, it is not applied only for this case, okay. So, for as a whole this vectorial addition, okay, it is applicable in many cases of this for this atom. So, actually this model was developed, this called vector model of an atom. So, this is one part of that. So, vector model of atom, very famous model, successful model, vector model of atom. Okay. Because considering this model actually when so far we are discussing only one electron system, hydrogen atom or hydrogen like atom, okay, or alkali atom, because it is it has similarity with the hydrogen atom, one electron system. So, these are the one electron system, but for many electron system, when atom is having many electrons, so each electron will have angular momentum, spin angular momentum, orbital angular momentum. So, then also for individual electrons, they have this momentum, whether they are coupled or individual. So, that question also will arise, and we will see that yes, they are coupled, and following the vector model, one can explain the structure of the atom of many electron system. Okay. So, atom having many electrons, for that this vector model is very successful model. So, this under this model one can consider that we found this total angular momentum from L and S of a one electron system. Okay. So, for L, this the L equal to L H cross, for S H cross. So, this J is called total angular momentum, and this similarly the J will follow the same way if you proceed. So, now another angular momentum, this total angular momentum. So, this also one can write the same way, J H cross. Okay. Now, what will be the value of J? So, this J is total angular momentum, the J value it will take L minus S to L plus S. Okay. It will take L minus S to L plus S. Now, if so here let me discuss more this how they are coupled, how this L is coupled. So, it is telling that this L will pieces taking J around the J, taking J axis, it will pieces. Okay. It will pieces, yes, J will pieces. I think I should draw symmetrically. So, it form a cone basically. So, about this axis J will pieces like this. Okay. So, J will pieces L will pieces taking the J as a axis. So, around the J L will pieces, around the J S will pieces, S will pieces. Okay. Around the J S will pieces. So, thus they are coupled with J. So, due to this precession they are coupled with J. So, J value I have as I told this, it can take L minus S to L plus S. So, then if I come to the similarity, next one is basically ML. So, ML value, ML equal to, it is nothing but space quantization, and I think it's the how it is, it came, it's L cos phi, right, that was quantized. So, that was ML H cross. Similarly, S cos phi, it is MS H cross. Here also that J cos phi. So, this is about a about a constant direction, right, in space. Okay. So, you can take as a field direction, say magnetic field direction. So, they are making angle this phi, this also making angle phi, but its phi is variable. So, initial angle may not be same, but they are in space. So, space quantization. So, j cos phi equal to m j h cos. So, is the since angular momentum, all are angular momentum. So, it will follow the we can follow the same way for all cases. So, what are the ML value? ML value can take minus L to 0 plus L. So, 2L plus 1 number of ML value. Similarly, S value, that is MS. So, it can take minus S2 plus S. Since it is half, so it will also take 2S plus 1, 2S plus 1. Since S is half, only this value is allowed for 1 electron. So, it will be MS will be 2, plus half and minus half. Okay. And then similar way one can write MJ, it will take value minus J2 plus J, it will have also 2J plus 1 value, it will have also 2J plus 1 value. Now magnetic moment for ML. So, this so the magnetic moment, as I mentioned, this it is just opposite direction. We write for L corresponding L, this mu L. Okay. It will be in opposite direction. Similarly, it will be in opposite direction, this mu S. Okay. This also it will be in opposite direction J. So, it will be J in opposite direction. So, later on I will see magnitude. So, this is mu J, this is mu J, right. So, here what relation we got? Mu L equal to L mu V, L mu V, L mu V. So, let me write here GL and mu S was GS S mu V. Okay. Similarly, mu J it will be GJ J mu V. In same way I have written, So, GL value is basically, we have seen this is 1, GL value is 1, GS value is taken this. So, this G is called G factor, or splitting factor, it is called G factor or splitting factor. Why it is called that we will see later on. So, G factor, G is called G factor. So, G is called basically G factor or splitting factor. Okay. This is called G factor or splitting factor, right. Now, if I consider, so this I have seen here. Now, here this one is GS, we have taken 2 for experimental agreement, because mu S you have seen this electron, this due to spin, this magnetic moment, intrinsic magnetic moment is basically mu B. So, S is half, G S 2, so it is mu v, and here it is L mu v for L equal to 0, it is 0, L equal to 1, it is mu v, L equal to 2, it is 2 mu v, etc. Okay. But here we will discuss later on, and let me first find out what will be the value of G j, what will be the value of G j. Okay. G j value is not 1, 2 or 3, it is different value. So, G j value I can write now, but I will derive it. G j it is basically 1 plus j square plus a square minus L square divided by 2 j square. Okay. G j value is 1 plus j square plus a square minus L square by 2 j square. So, that how it is coming, that I want to show now. So, for that, so this is J corresponding magnetic moment mu j. Now, this is L corresponding magnetic moment mu L. This magnitude will be same in terms of mu v. So, this is mu L in opposite direction, and this is S. So, corresponding sorry. So, whatever the magnitude here is equal to half basically. So, but here it is not half mu v, it is mu v. So, this magnitude will be double. Okay. In terms of mu v, magnitude will be double. So, this and this. So, this more or less this one will be the mu s. Okay. Now, vectorial addition of these two, will give you vectorial addition of these two. If I and then this yes, more or less it is same. So, vectorial addition will be this, okay, and then if I just so here you can see the direction of mu j and direction of the vectorial addition of this mu s and mu l are not same. So, this we tell generally mu ls. So, mu ls is different from the mu j. Here this vectorial addition will be giving j and corresponding mu j, and now if we consider the individual mu l just opposite to L, mu s opposite to s, now resultant of this mu l and mu s is mu ls. Okay. Then that magnitude and direction is not same as mu j, it is different. Okay. So, I think I will erase it. So, now you see if I want to find out mu j, so mu j, so mu j, now we can take the component of mu s along this j direction, all right. So, mu j equal to we can write mu s, let me write first mu l, I can write mu l component of this along the mu j direction or j direction. So, this will be mu l angle between L and j, angle between L and j, right, plus mu s angle between s and j, mu s angle between s and j, okay, or mu s and mu j. So, that will be s j, okay. So, from here mu l equal to L mu v, right. So, GL is 1, okay, plus okay, this cos L j. So, cos L j. So, if you take this triangle, okay, so this cos value, you know, this it will be L square. So, what are the so here L s and j triangle, if you consider L s and j. So, here what will be the angle? Cos L j and s. So, that angle you can write this angle opposite to this, which one is angle? L j, this is the angle, right, this is the angle, and this will be s, one is L, one is j, and this will be the s, right, this will be the s, okay. So, this will be the s. So, cos j L, L square, this cos j L, this will be L square plus j square minus a square divided by 2 j L, right, plus mu s. So, mu s is, I can write s mu b, g s s mu b, right, that we have written g s s mu b. So, g s s mu b. So, g s is 2, s is half. So, that is why we write this is only mu b, or okay, no. So, we will write 2s mu b, g s mu b. So, s is half, s is there, g s is 2. So, I am writing 2s because g s is always 2. So, then angle cos s j. So, this you can consider this one. So, j s and opposite one is L. So, this angle is just opposite to L. So, it will be I can write here. So, plus 2s mu v, s j. So, I will get a square plus j square minus L square divided by 2 s 2 s j, yes, 2 s j, okay. Now, if you just simplify it, it is done. Just you simplify it one step, you will get. So, you have basically mu v, and then you will see from here itself. I think J will come because J is everywhere is there, J is everywhere is there, and from here you will get Gj, some constant J mu v, and Gj will be this. So, I am not doing that next step, just please do it, and then you will see Gj J mu v, where Gj will be 1 plus J square plus A square minus L square divided by 2 J square. Okay. So, if you just do the next step, so I have derived it. Okay. So, I got the relation for Gj, and now everything in our hand. I think these are the sufficient quantum number in our hand, and next we will try to see whether this number of quantum quantization can explain the fine structure of atom. So, I will stop here. In next class I will explain.